Today I want to give you a detailed description of AES, the most widely deployed symmetric-key encryption scheme. There is a wealth of material about the security of AES, but this would take too much time to cover. So I won't talk about AES security, but instead only show you the inner workings of AES. You will likely find this presentation a bit dry. Nonetheless, I think it's worth spending the time to understand how AES works, given its prominence in real-world cryptography. AES is a block cipher adopted in 2001 as a US government standard. AES has 3 key lengths, 128 bits, 192 bits, and 256 bits. The block length is 128 bits for all the 3 key sizes. These lengths address the 2 main problems with DES, namely a key length of only 56 bits and a block length of only 64 bits. As of 2024, no attacks have been found that are significantly faster than exhaustive key search. In this lecture, I'll describe AES for the case where the key length is 128 bits. Thus, plaintext blocks, ciphertext blocks, and keys all have bit length 128. AES is an example of a substitution-permutation network, which I'll define next. I'll first tell you what a substitution-permutation network is before proceeding to describe the AES encryption algorithm. A substitution-permutation network, or SPN, is an iterated block cipher. Encryption takes place in a number of rounds, where a round consists of a substitution operation followed by a permutation operation. The components of an SPN cipher are the following. N is the block length in bits. L is the key length in bits. H is a number of rounds. There is a fixed invertible function S, also called an S-box, which maps bit strings of length B to bit strings of length B, where B is a divisor of N. There is also a fixed permutation P on the numbers from 1 to N, and a key scheduling algorithm that determines subkeys K1, K2, up to KH plus 1 from a key K. I'll note that the block length, key length, number of rounds, the S-box, the permutation, and the key scheduling algorithm are all public and fixed. The only secret in AES is a key K that is selected by Alice and Bob. Here's how encryption works in a substitution-permutation network. Let A be a plaintext block. Encryption takes place in H rounds. In each round, the ith subkey is added to A, and then the substitution is applied to A, B bits at a time. Recall that B divides N. This is the substitution layer. Then, the bits of A are permuted according to the permutation P. Finally, the last subkey is added to A to give the resulting ciphertext. Decryption is just the reverse of encryption. Note that all the operations are invertible, and so someone who knows a secret key can recover plaintext from ciphertext. AES is a substitution-permutation network where the permutation operation is replaced by 2 invertible linear transformations. All operations in AES are byte-oriented, so they work on individual bytes. For example, B equals 8, so the S-box maps 8 bits to 8 bits. This allows AES to be efficiently implemented on software platforms. The block length of AES is N equals 128. Each subkey is 128 bits. AES accepts 3 different key lengths, namely 128 bits, 192 bits, and 256 bits. The number of rounds depends on the key length, namely 10 rounds for 128-bit keys, 12 rounds for 192-bit keys, and 14 rounds for 256-bit keys. I'll only present AES 128, where the key length is 128 bits, and encryption takes place in 10 rounds. Recall that a block in AES is 128 bits long, or 16 bytes. Each round of encryption updates a variable called state, which is a 4x4 array of bytes. State is initialized with a plaintext block. So initially, the 16 bytes of plaintext are written as the 4 rows of the state array. The AES round function uses 4 invertible operations. These are AddRoundKey, which mixes a subkey with the state, SubBytes, which is application of the S-box to the bytes of the state, ShiftRows, which is a permutation, and MixColumns, which is an invertible linear transformation. After H rounds of encryption are completed, the final subkey is XORed with state, the result being the ciphertext. The AddRoundKey operation simply XORs the bytes of the state with the corresponding bytes of the subkey to get the bytes of the new state. SubBytes takes each byte in the state and replaces it with the output of the S-box as shown in the figure. Recall that the S-box is a fixed, public, invertible function which maps bytes to bytes. The S-box is a nonlinear function. I'll next describe the AES S-box. You'll see that its description is algebraic in nature. The algebraic structure of the S-box was used to analyze the security of AES against certain kinds of attacks. I won't be saying anything about the security analysis. I need to define the finite field GF2 to the 8. GF stands for Galois field. The elements of the finite field GF2 to the 8 are the polynomials of degree at most 7 in Z2y. Z2y is the set of all polynomials where the indeterminate is y and the coefficients come from the integers modulo 2. The coefficients of polynomials are added modulo 2. So 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 0. Addition and multiplication of these polynomials is performed modulo the irreducible polynomial f of y, which is defined to be y to the 8th plus y to the 4th plus y cubed plus y plus 1. This polynomial is fixed for AES. In the following, we'll interpret an 8-bit string A, whose bits are denoted A7, A6 down to A0 as coefficients of the polynomial a of y of degree at most 7, where the coefficients A7, A6 down to A0 are the bits of A, and vice versa. And so we can think of a byte as a polynomial over Z2 of degree at most 7, and vice versa. Here is an example. Let A be the byte 111-01100. In hexadecimal, this is EC, because the first 4 bits of A are 1110, which in decimal is 14, and that corresponds to the hexadecimal digit E. Similarly, the second 4 bits of A are 1100, which in decimal is 12, and which corresponds to the hexadecimal digit C. Let B be the byte 0011-1011, which in hexadecimal is 3B. And so the polynomial corresponding to the byte A is a of y equals y to the 7th plus y to the 6th plus y to the 5th plus y cubed plus y squared. The missing powers of y correspond to the zeros in A. Similarly, b of y, the polynomial corresponding to the byte b, is y to the 5th plus y to the 4th plus y cubed plus y plus 1. Here is an example of addition. Adding the 2 bytes a and b corresponds to adding the 2 polynomials a of y and b of y. And so a of y plus b of y is y to the 7th plus y to the 6th plus y to the 4th plus y squared plus y plus 1. Notice that when a and b are added, the y cubed terms sum to 2 times y cubed, which is 0 since 2 is congruent to 0 modulo 2. Recall that coefficients of polynomials are integers modulo 2. In hexadecimal, we can write EC plus 3b equals D7. D7 is the hexadecimal representation of the byte corresponding to the polynomial a plus b. Here's an example of multiplication. I can multiply the bytes a and b together by first multiplying the corresponding polynomials and then dividing by f of y and taking the remainder. You should check that the polynomial product of a and b is this degree 12 polynomial. Then check that when this degree 12 polynomial is divided by f of y, the remainder is the polynomial y to the 7th plus y to the 6th plus y cubed. Remember that coefficients are added and multiplied modulo 2. Hence, a times b is this byte, which is the byte representation of the polynomial r of y, which in hexadecimal is C8. So, I can write that the byte EC times the byte 3b equals the byte C8 in GF2 to the 8. Here is an example of inversion. The inverse of the byte EC is 5d. And that's because the product of the polynomials corresponding to EC and 5d is the identity element 1. You can check this by multiplying EC and 5d and confirming that you get the polynomial 1. I'm now ready to define the AES S-box. Here is an algebraic description of the S-box. Let P be a byte, which we can consider to be a polynomial over Z2 of degree at most 7, so an element of the field GF2 to the 8. If P is non-zero, then Q is defined to be the inverse of P in the field GF2 to the 8. So the element in GF2 to the 8, which when multiplied by P equals 1. If P is 0, we just define Q to equal P. The inverse function is used in the S-box because it is a nonlinear function. Its algebraic properties can be used to ensure that AES has certain desirable security properties. Let the bits of Q be Q7, Q6 down to Q0. I'll then multiply this fixed 8x8 binary matrix with this vector whose entries are the bits of Q and add this fixed vector all modulo 2. The resulting bits are called R0 up to R7. These are the bits of R, which is defined to be S of P. So the AES S-box maps the byte P to the byte R. This function is a nonlinear function since inversion in the field GF2 to the 8 is nonlinear. Here's an equivalent definition of the S-box in the form of a table. For example, S maps the byte A8 to the byte C2, because the table entry indexed by A and 8 is C2. In terms of binary strings, S maps the string 10101000, which in hexadecimal is A8, to the bit string 11000010, which in hexadecimal is C2. So the AES S-box can be easily implemented using a lookup table. The third AES round operation is ShiftRows. This operation shuffles the bytes of the rows of the state. The bytes in the first row of the state remain unchanged. The bytes in the second row are shifted one position to the left cyclically, so the leftmost byte becomes the rightmost byte. The bytes in the third row of the state are cyclically shifted 2 positions to the left. The bytes of the last row are shifted cyclically 3 bytes to the left. The fourth AES round operation is MixColumns. The purpose of MixColumns is to mix up the bits in the 4 bytes of each column of the state. Like the S-box description, the description of MixColumns is algebraic in nature in order to facilitate analysis of AES security. Recall that each byte of the state can be interpreted as an element in GF2 to the 8. So we'll interpret the 4 bytes in each column as coefficients of a polynomial in X of degree at most 3, where the coefficients are in the field GF2 to the 8. The MixColumns operation is then defined as follows. We multiply the polynomial corresponding to a column of the state array by the fixed polynomial c of x, which is defined to be 03x cubed plus 01x squared plus 01x plus 02. Note that the coefficients of c are the bytes 02, 01, 01, 03, written here in hexadecimal, and so can be considered to be elements in GF2 to the 8. We obtain a polynomial of degree at most 6, whose coefficients are in GF2 to the 8. When performing this multiplication, coefficients of the two polynomials are added and multiplied as elements in GF2 to the 8. We then divide the resulting polynomial by x to the 4th minus 1 and get a remainder of degree at most 3. Lastly, we interpret the 4 coefficients of this remainder polynomial as the 4 bytes in the result of the MixColumn operation. Here is the multiplication by c of x operation in a bit more detail. I'll let a of x be this polynomial in x of degree at most 3, where the coefficients of the polynomial are the 4 bytes in a column of the state, interpreted as elements in GF2 to the 8. Let c of x be the polynomial 02 plus 01x plus 01x squared plus 03x cubed, where 01, 02, and 03 are elements in GF2 to the 8, written as hexadecimal strings. To compute this product of a of x and c of x, we'll first compute the polynomial product of a of x and c of x. Let's call this result d of x. We then divide d of x by x to the 4th minus 1 and get the remainder polynomial r of x. This division can be performed as follows. Replace the x of the 4th term in d of x by 1, the x of the 5th term in d of x by x, and the x of the 6th term by x squared. After simplification, in other words, after adding the terms of the same degree together, we obtain a polynomial r of x of degree at most 3. Then a of x times c of x is defined to be the remainder polynomial r of x. For example, let a of x be this degree 3 polynomial written in hexadecimal. You can check that a of x times c of x is this degree 3 polynomial, which as a hexadecimal string is 1a, a4, d3, e5. And so the result of applying the MixColumns operation with this column of the state is this column.
You should try this example yourself, by hand, to make sure that you fully understand the MixColumns operation. There is a handout on the course webpage, Cryptography101.ca, that explains how the MixColumns operation can be quickly done using lookup tables for multiplication by the GF2 to the 8 elements 02 and 03.
Here now is the AES encryption function. Recall that the AES secret key k is a bit string of length 128 bits. From k, the key scheduling algorithm is used to derive h plus 1 subkeys denoted k0, k1 up to kh. Each subkey is a bit string of length 128 bits. We initialize the state to the plaintext block and add the first subkey k0 to the state. We then perform h-1 rounds of encryption. In each round, we apply the S-box to each of the 16 bytes of the state. Shuffle the bytes in the rows of the state by applying the ShiftRows operation, and then we mix up the bits in the bytes of each of the 4 columns of the state by applying the MixColumns operation. Lastly, we add the next subkey to the state. To conclude, we perform one more round of encryption, but note that the final round omits the MixColumns operation. This omission is for technical reasons to facilitate hardware implementation of AES. We expect that each ciphertext bit depends on all the bits of the plaintext, and also that the ciphertext bits are complicated functions of the plaintext bits and the secret key bits. So, one can expect that AES encryption has Shannon's properties of confusion and diffusion. Since all the AES round operations are invertible, ciphertext can be decrypted to get plaintext by applying the inverses of the round operations in reverse order. The decryption algorithm is shown in the slide, but I won't explain it any further. To complete the description of AES encryption, I need to show you how the subkeys are derived from the secret key K. I'll do this for the case of 128-bit keys. Recall that for 128-bit keys, AES has 10 rounds, and so we need to derive 11 subkeys from the secret key K. The first subkey K0 is defined to be the AES key itself. I've written K0 as a sequence of 4 32-bit words R0, R1, R2, and R3. The second subkey K1 is derived from K0. The third subkey K2 is derived from K1, and so on. Here's how the 4 words of the subkey Ki, where I is between 1 and 10, are derived from the 4 words of the previous subkey Ki-1. First, the last word is passed to this function fi, which produces a new word, which is then added to the first word. The result is the first word of the ith subkey. This word is added to the second word of the input to get the second word of the output, and so on. Lastly, here is a description of the key schedule functions fi. Each fi maps words of bit length 32 to words of bit length 32 and is defined as follows. The input is divided into 4 bytes A, B, C, D. These bytes are left rotated to give a word B, C, D, A. Then the S-box is applied to each byte to give the word SB, SC, SD, SA. And finally, the leftmost byte is XORed with the constant byte Li, and the resulting word is defined to be F of I of the input word. Here are the 10 constant bytes Li, from L1 up to L10, one constant for each round of key scheduling. This completes my description of AES. A lot of thought and analysis went into the design of AES. If you would like to learn more about this, you should read the book The Design of Rijndael, written by Joan Damon and Vincent Ryman, the designers of AES. Here are some performance numbers for Cha-Cha-20, Triple DES, and AES. The numbers are from a 2018 implementation on a particular platform. One can see that Triple DES is significantly slower than Cha-Cha-20 and AES, and Cha-Cha-20 is faster than AES. However, many processors, including those from Intel and AMD, now have special instruction sets for AES operations. The instruction set is called AES NI, NI standing for New Instructions. As illustrated in the last 2 rows of this table, the customized AES implementations are much faster than AES implementations that are done from scratch in software. For this reason, AES is generally preferred over Cha-Cha-20, especially on platforms where the AES NI instruction set is available.
A motive operation is a method for using a block cipher to encrypt a message of arbitrary length. We'll study the ECB and CBC modes of encryption in V2F, and then conclude Chapter 2. Have a great day!